Welcome back, everyone, and today we're going to do the final video about splines and Bezier curves. So now that we can create splines and curves and have an editor to manipulate them, we can animate on them and we're able to extrude on them. Now the last thing we really need to do, especially if you're extruding, is to simplify the extrude, what you're extruding. Because originally what we're doing is we're always taking a curve and then dividing it up by an equal amount of parts. So if we say, subdivide a curve by 10, it makes an equal 10 parts, pieces out of the whole curve. That can make the mesh a little bit more low poly looking, because certain parts of the curve will be more boxy because there's not enough vertices to kind of smooth it out. So here's an example of what we're going to be doing today. And as you can see, instead of being, like the sampling is evenly divided, it's actually more closer to where the curvature is. And anything that's straight line, the gaps get wider. So as an example, as we're modifying the data, as you can see, the more curvy parts get more sampling, and the parts that are more straight lines, less sampling. So this is what I mean by curve or Bezier simplification, because we're just simplifying the overall amount of sampling that we need to do. The theory behind sampling is actually pretty easy. The notion is that it only works really well when you do it curve by curve. So if we're doing the whole spline, where you might have more than one curve tied together, you kind of have to do it per curve. So you have to loop through each curve and then do a kind of a smart subdivide of it. You got to simplify the points. So the theory behind simplification, like one method of it, is that we have our curve. Let me just modify this. We know this point and we know that point. We want to get the middle point. So we know them. We can get the midpoint because remember, we get Bezier curves by using time. So over here is 0, over here is 1. So the middle point will be 0.5. So we get to 0.5. We say, okay, give us what position on the curve is 0.5. So it'll be around here. So the notion is you take this point, the midpoint, and then the end point, and then you calculate the angle that it creates. And in this instance, it would actually create a straight line, which would then stop the simplification. But in the algorithm I put together, I actually take it a step further. I subdivide twice. So first I divide the curve into halves, and then I start to simplify the halves. So in an instance of, like, let's see right here, like if I have the midpoint here, you have the end points here, this kind of creates kind of like a 45-degree angle. So so what I'm looking for is straight lines. So if it's not a straight line, save that point, take the left and right and subdivide it. And that's what you keep doing. If the angle, if the midpoint angle is like over a certain threshold, which is basically greater than basically a straight line, subdivide it. So we keep subdividing it until the point we just have a bunch of straight lines, and that's exactly what we want. Just like this. Trying to get as many straight lines as possible. So we can have a line there, and really that's because the curve is a little, there you go. So that's pretty much just about right. That's the picture. So when we extrude, it'll go from here to there and no in between. So I guess that's enough demoing. Let's start looking at the source code. The first thing we're going to do is go into core, and we're only going to do some minor changes. Only 2 changes in the core today. First thing we got to do is go to our vec3 function, and we have to fix magnitude because the order of of subtraction is off, so it's backwards. So there's a little bug, and that's what we got to do is just flip it around. We subtract this from the vector that we're bringing in, as opposed from the vector we're bringing in minus this. So that's one. And then we have a new function called square magnitude, which is the same thing as regular magnitude minus the fact that we do not do a square root. That's why it's called square magnitude. It's twice. The reason why I have this is because I need to measure distance between points, because we're only going to subdivide if the line is a minimum length. If the line is shorter than it, then we can't subdivide anymore, because then might be stuck with infinite loop. So instead of using magnitude, because we don't need to be exact with our distances, so to save one mathematical operation, you can use square magnitude, which will give us the distance but squared. So we don't do the square root at all. If you're doing a lot, it just helps with the CPU, just optimization tricks. That's all it is. So like I said, if you don't need exact measurements, then you can kind of get away with square magnitude instead of. But if you need exact measurements, then use magnitude, where it gives you exactly the actual distance between 2 points. So now we go to spline. In our spline mesh, I'm replacing our process spline function. Let's see what it used to look like. It used to be very simple. And our new spline process is a little bit bigger, but I comped it out because we're going to add this later. What this thing does is now we're going to go one curve at a time. So if we have our spline that has 2 curves, we're gonna run subdivide curve twice. Like, remember in the beginning I said we need to take each curve at a time to properly subdivide it and get a really good smooth sampling, simplified sampling. So we're going to do this one curve at a time. We're going to get its position. Well, what the subdivide does, because I'll show you that function a little later. So basically, we're just going to subdivide. We get the list of time, and then we kind of just loop through and kind of convert it from the curve to the whole spline as a whole. That's what this math is doing. It's kind of like mapping it from from a single curve all the way up to where it belongs in the entire spline. We get we get its position, and we're going to save that position to our array. And then we do our update. And this is just to do the points. Everything that I have commented out is for extruding, and I'll uncomment it later, and we'll see how it actually looks when we have things in there. Another function we're going to be adding to is our spline. We got get curve position, because get position again does time based on the entire spline. So get curve position, basically you have to tell it which curve you're trying to access, and then gets the time of just that curve alone. Like I said, since we need to sample each curve independently, that's why we need this function. And then we go into our subdivide, which also belongs to spline, which does all the fun stuff. So we have a lot of variables that we need, and normally this is done as a recursive function. But since I don't like recursive functions that much, I always tend to go with stacking. So this way it's a single function call that loops until it's done. I just like that method over recursion. Even though recursion can make a function look smaller, it's less code, there's more processing, because you have to then have functions calling functions, and they pause because their sub-function calls are waiting to complete. So I started programming many years ago, like 20 years ago, and recursion at the time for like Visual Basics, Visual Basics 3 had up to 32 levels. So recursion was something you can only do when you knew there's only a small amount of, when you had an idea of how deep the recursion will go. If you know that's going to go past 32 levels, your entire application will crash, and you have to use stacking. So since I learned that limitation doesn't really exist anymore, so there's no reason not to do recursion. It's just I'm an old programmer that just likes these old tricks because they're very optimizable. They're more the only difference is I'm trading a little bit more speed, because I'm not calling functions on top of functions on top of functions. It's a single function with a single loop. So I'm trading all that processing for wasting up more memory. Actually, in some ways, I'm actually using less memory, because if I call this function repeatedly, I will be constantly adding more variables to the stack. So, well, not this stack, just like memory stack, like the heap and the stack. And I think in the long term, with heavy mathematics, with recursion, you kind of end up using more memory than you probably do. Like this way, with the stacking method, I'm only creating all these variables once, and I'm reusing them. So I guess in the long term, you get more speed out of it. You use up less memory. It just makes a slightly more complicated function. That's all. So so I regress. I just wanted to show you why because normally you would always see people do this in as a recursive function. I'm doing this as a stacking function. So there's the reasons why I'm going into the more complicated route. So angle threshold is basically the angle that we're going to be testing based on the dot product. This works really well. It's basically checking to see if it's a straight line. So if you're just barely more than a straight line, I'm going to subdivide you. That's you can try lower numbers, but they don't work very well. If you go like lower numbers like this, then you get better subdivision. You get like more finer subdivision, but at 999 actually works pretty well. This is the minimum distance that the 2 points need to be before we even test for subdivision. Like I said, if we keep subdividing by halves, it's infinity. You can get really close to infinity. So just put a bare minimum. So this way we do less processing, and we're doing pretty good. We don't want to go near infinity. So that's kind of just a stopgap. Our stacks, this is where we're going to save our all the subdivisions we're going to be testing, and this just our array. And to start with, we're always going to return the beginning and the ending points, the two red dots on on the editor. And then we have a bunch of variables. We're going to be testing our left and rights, the midpoints, the start points, the end points. And then we can have vectors for left and right based on the positions. So like I said, originally, normally in the algorithm I originally found, we start off with 0 and 1, and then we let the algorithm process that. But since I start off with a sine wave, that creates a straight line, so it never subdivides. It automatically assumes it's a straight line. So a simple solution, which seems to work pretty well, is just automatically subdivide it and then subdivide it again. So this is where I'm doing it. So I know 0.5 is my halfway point, so I'm going to do this the left side of the half of the curve and the right side of the half of the curve. And this is, so we start off with two things in a stack for processing. And we loop until the stack is empty, until we ran out of stuff. And I have this in there because I was getting a lot of infinite loops. So there's some debug stuff here to make sure I don't stop crashing the browser. But they're all commented out because we don't need it, because this function now works really well and no more infinite loops. So we pop the stack, we get our start and end positions, and then we use our get curve position to get the actual vector positions. So we know where they are. The points exist in world space, and then we just calculate the distance and make sure the distance is less than. Well, if the distance is less than the minimum, we continue. That means we don't continue this loop any further. We go back up here and continue. I use continue a lot. Some people don't. Some people just put if statements and sub-if statements. I try to avoid a lot of sub-if statements. So continue is a good, good thing to start using, because I don't see a lot of people using them a lot of times in programming. So now that we know that we are at least at the minimum length of our 2 points, we then calculate our midpoint. So 0 and 0.5, our midpoint would be 0.25. So that's kind of like during this process, we're processing this item. That's where our midpoint is, and then we get its position, its world space position. Once we have its world space position, we're going to calculate the left side and then normalize it. We're going to create the unit vector, basically. It's kind of like the direction vector from the midpoint. We get the right side, we normalize it, and then we get the dot product. Remember, if we're going to use a dot product to get a proper angle, make sure the two vectors are unit vectors. They're normalized. They're so this way you get a nice value between -1 and 1 when you do a dot product. I'm still new to a lot of this math, so in case you're new to it too, I'm just reminding you things I'm learning how to do, all this mathematics. And if the dot product is greater than like the bare minimum, what I consider a straight line, we we save that midpoint to our list, our array that we're gonna return back of all the points or all the times samples that we're getting, and then we basically we take the current position, like in the instance of this, we then cut that in half and add it to the stack. So this way we're subdividing that division and then processing further. And then when all said and done, we do a sort. The reason why I did it this way, because we're saving time. So we'll keep subdividing until we get all the times that we need on the curve. Since we're saving time, we can quickly put it in order just by running a sort routine. So we sort it, and now everything is in the proper order between 0 and 1. And then when we want to process that list, we just process it in the exact order, as we do up here. So here's the subdivide thing that we just looked at. We get the array and we just loop, and that's it. And we just, since we have that time from array, divide by t core, whatever, we calculate the new time, and there we go. All right, so now we go to our HTML page. Song by Leo, Pink Try. I was listening to music while I was writing this. Let's see. I don't think much has changed, really. Really, it's pretty much a lot of the same things. I'm using the DOM shader for now. Spline is set to just 1. And pretty much all the same. Nothing has changed, really. So, and it creates this. So now let's go back to Spline. Now we don't want to save this vert anymore. Now we want to start extruding our shape. So we're going to fix that in our process spline. Now that we have our all our vertices, let me just save it. So this way you get to see what it looks like. So there you go. There's all our points extruded. Now that we have all our points, we need to triangulate everything. You know, we have that function that existed from the previous lesson. And we set this to 8 because we want to use indexes, because we need to use indexes. We could put any number because it'll resize automatically. And then that last thing we need to do is change our draw mode to triangle strips. Let's click save, and that should create the shape we want. Now if we go back to here, I already had all these commented. That goes away. Put our low poly in there, our low poly material. Save. Refresh. And ta-da. That's right. It's using a null function. Let me fix that. I keep forgetting about that. Where is it? Greater than 0.99. Oops, wrong command. That will fix the little triangles. Ah, there you go. Much better. So now, there we go. So, there you go. And there it is, simplification. So the more curvy parts are subdivided better, and the straight line is pretty much just a straight line. This looks a lot better than having everything subdivided evenly. So the curve would, you know, the curve would be less smooth. It would be more blocky, because it would have to subdivide everything by 10 or whatever samplings you want. You know, if you wanted to get something smooth, you do like a sample of like 30 samples. You'll give you a nice smooth curve, but then you have a bunch of vertices that are wasted to subdivide this straight line. So this is where simplification can happen. If you want to simplify things even further, like, you know, if you still feel like it's a little bit too blocky, you know, subdivide. Let's do like 999. Click that. Refresh. This should make a nice. It should subdivide a lot even more smoothly. Kind of hard to tell without the dots. By the looks of all the triangles, you kind of see a lot more sampling happening. That's because I changed the threshold. So the threshold's smaller, so it ends up subdividing further than normal. But this looks pretty good. You know, it curves really nicely. It's fairly smooth. I'm sure if you tweak it some more, you can improve its smoothness. But so yeah, that's simplification of spinal curve. Ooh, that looks nice. That's some nice animations. That's kind of neat. Just slowly rotating. That's kind of neat. See, now I kind of feel like writing something that makes that effect. That's a pretty cool effect, though. I guess the idea is you go up the array and then you slowly rotate everything. But whatever. So there we go. There, that looks nice. That's pretty smooth, though. I like it. That looks really smooth. I guess since I upped it, it's creating a lot of samples automatically. Yeah, it's pretty smooth, I think. That looks pretty neat. So there you go. Simplification. I know there's errors there. It's kind of hard to figure out where the bugs are when it comes to it tells me what it is, but the this data buffer, no data, that means there's a single frame while we're modifying everything where we have like no vertices, and I'm trying to find. It's kind of hard to find the exact position where that data. There's like somehow there's a like the exact position, like the exact numbers to get it, so to generate the error, so I can really see what's causing it. But overall, it works pretty well, even though certain instances, if I get rid of it, it's hard to repeat. Yeah, it's just really hard to repeat it. It's especially when you're editing it in real time. I probably had like a really weird looking curve. But again, that's what the error is really about. That at some point during during that frame of modification, it just didn't generate any vertices for some reason. And then I'm trying to render something, and there's no data in the buffer because we wiped it clean, and then passed in nothing. So that's it. So that's it for splines and Bezier curves. We're not going to deal with that anymore. The next lesson, I'm going to deal with spheres and building a sphere by using a lathe. I think that's how you pronounce it. Lathe, L-A-T-H-E. It's similar to extruding, except we kind of just loop things in a circle on a certain axis. We say, okay, here's a list of vertices, and just repeat them by rotating them on a certain axis. This way, like we create like a curve, and we repeat the curve around 360 degrees by a certain amount of intervals, and that creates a sphere. So I'm gonna be doing that in the next lesson, and then after that, maybe doing a little bit of wireframe. I was gonna do both at the same time, but I didn't really want to waste too much, make the video really big for the next one. I'll just break it down for you. Here's a lathe, creating a sphere, and then we're gonna do wireframe and render the sphere with a wireframe, because wireframes are a little complicated in WebGL. So I'll explain it further. But here you go. Hope you enjoyed it. Hope you're having fun. We can do really cool shapes now. See you guys at the next lesson. Like, subscribe, comment, the whole spiel. Again, hope you have fun. Goodbye.